the polling went the exact way that I believed it would go, in the sense that the way that the polling was flipped in the other direction, because the polls are not being collected properly. They're still collecting polls by calling people. They're still collecting polls by hoping that people pick up their phone and answer. And I'm sorry, that's not going to cut it. It's not going to cut it when you're off on Florida by 6 points. It's not going to cut it when you're off on Pennsylvania by 7 points. It's not going to cut it when there were a lot of Senate races where the guy was supposed to win by 5 or 6 points. He ended up losing by like 3 or 4. It's like, why is the polling so wrong? No. The polling, the numbers are not wrong. They can only report on what they collect. The way that they collect the data is wrong. No one wants to listen to me, apparently. I don't know. But it is what it is. We'll see what happens. I got this whole thing mapped out. I'm going to be doing a recap video on my personal YouTube soon, but I have all of the remaining states that have not been called, Senate races, House races. I got them all right here. And I got my projections, so I feel pretty good about them. I don't know. There's one Senate race, not Senate race, House race. There's one House race in Iowa. 89% reporting. Look at the difference. That's amazing. I love it so much. Anyway, back to this. Get rid of this. Yeah, there we go. And I'm going to bring this up. Okay, so what are we doing today? Today, I am going to be introducing the next unit, or not unit, the next main chapter that we're going to be covering. I introduced it a little bit before the week off, but we're going to deep dive it today. We are severely going to deep dive it today. That's going to be awesome, mainly for me. So let me start just by asking you the following questions. I'm going to assume that you are somewhat familiar with the athletic events involved in track and field. Maybe not an expert, but somewhat familiar with the events in track and field. 2 events in particular, one event being the long jump, and the other one being the shot put. Now, the long jump person's got to run, come up to like a little spot on the ground, I don't even know, and then jump, and then like bicycle kick or something, and then land on the ground as far as they can. What athletic attributes do you need to have in order to be decent at the long jump? What capabilities do you need? Or if I were to look at someone like, yeah, that's someone who could be like really good at the long jump, what physical attributes might they have? Maybe long legs? For what reason? When they're jumping through the air? Absolutely. You know, because they got long legs, they can stretch. Absolutely. What else? Because my wife has long legs, but she would be terrible at the long jump. What else do you have to have? That's it, I guess. You gotta have speed. You definitely gotta have speed because you're running up, you're building up your momentum, and then you gotta have, you gotta have muscles in those legs. You gotta have jumping ability. Those are the 3 main things, really. It's like you run, you jump, and then you stretch as far as you can go. Now the shot put. The shot put, you pick up this big old ball. I looked it up. For the men's events, it's 16 pounds. You pick up the 16-pound ball, which is basically the weight of the largest bowling ball you can get. You gotta put it up to your cheek or whatever. And then, what physical? Oh, look at it. You have to have. Sorry, she's answering the questions I didn't say her, so that's all good. What physical attributes do you need to have in order to be decent at the shot put? I mean, I've seen these Olympic athletes. They do not look like long jumpers. What's so different about a shot putter? Strong where? Arms, definitely in the arms. Maybe a little bulkier. Maybe a little bit, a little low sense of gravity almost, because you got to be like compact and you got to be explosive, where it's like she has a strong upper body. You got to be compact and explosive, where sometimes I think I've seen some of them do like a spin or something, and they go, that's the noise they make, I think. And then it goes as far as it can possibly go. If I had in this room right now a really good long jumper and a really good shot putter, if I had two athletes in this room, one who was really good at the long jump, one who was really good at the shot put, could you tell me who the better athlete is? I see all you shaking your heads no. Why? Why? I have two maybe world-class athletes. I don't know. Who's the better athlete? You're telling me? No, I can't tell you who the better athlete is. Why? So what does that mean? Ooh. Strengths are in different areas. Ooh. You ever hear the phrase comparing apples and oranges? Yeah. Oranges are disgusting. Fact. Thank you. Anyway, no. But comparing apples and oranges, you can't compare the two, because even though they are both fruit, just like these two people, imaginary people, are athletes, even though the apples and oranges are fruit, you cannot just compare them directly because they have different attributes that make them desirable for people to eat. You can compare apples to apples, which is kind of a dumb game. You know, it's a better game. Besides apples to apples, they have, it's not really junior, but it's like apples to apples with pictures. You know what I'm saying? My son loves it. He doesn't have to read a thing. Oh, we read him the words, but he learns vocabulary. Shut up. Anyway, the idea of comparing apples to oranges doesn't make sense, but apples to apples, yes. Gala to Granny Smith, yeah, you can compare those two because they're both apples. And yes, they have different attributes, but then you can compare them directly. We cannot compare a long jumper to a shot putter directly unless we do some kind of a conversion. For example, it's difficult to compare a set number of miles to a set number of kilometers until you convert one into the other. It's difficult to compare, like, question, when you get a jug of milk, what do they typically measure milk in? Say? Gallons. They measure it in gallons, which is like the English system, I think. But then when you go and you get a bottle of soda, what do they typically measure those in? Liters, which is the metric system. Like, what the heck? You can't compare gallons and liters directly until you convert one into the other. I'm not saying that we're going to convert the long jumper into a shot putter. I'm not saying we're going to convert the shot putter into a long jumper. Instead, we are going to take their numbers, their abilities in those events, let's say, the distances that they can throw or jump, and convert them to something else. Convert them to a standardized ruler in which we can actually do a true comparison. So if you would, ladies and gentlemen, if you do not already have them out, I'm going to need those notebooks out and open. My son, when he used to eat apples, he was like 1, and he only had like 4 teeth. And when he ate these apples, it was like his teeth would peel off the skin of the apple, and he wouldn't eat the skin. So when he was done eating the apple, there was always this pile of like little skin slivers of an apple sitting next to him. It was disgusting. Just for the sake of argument, when we get back on a AB schedule, a regular AB schedule, we should hopefully be back on track for what AP Stat has to offer. Obviously, because of this schedule, I've had to adjust the timing on how we do these things. Believe it or not, we're only a couple of weeks behind what I have typically done in the past. But we're in good shape. I want to compare these two athletes. Athlete A versus athlete B. Now, athlete A and athlete B. One of them will be better at the long jump, and one of them will be better at the shot put. That's just a fact. One of them is a really good long jumper, and one of them is a really good shot putter. Athlete A is able to do the long jump in 6.78 meters. Pretty good. Athlete B is able to do the long jump in 6.30 meters. Good for them. I gotta get the live chat up here on my phone while I'm doing this. Now, clearly, athlete A is the better long jumper. Now, let's just say they get these numbers on average, let's just say, for the sake of argument. Now, when it comes to the shot put, you can pretty much guess that athlete B is going to be better at the shot put. Athlete A can throw the shot put in 14.77 meters. And athlete B in 16.40 meters. 16.40 meters. Move that over a little bit. For those of you in the chat, I do have the chat open on my phone right here, so I can see what you're saying and shut up. So clearly, athlete A is better in the long jump. Clearly, athlete B is better in the shot put. Now, don't answer this. Don't answer this question. This is more rhetorical. I really want you to think about it. Who is the better athlete? You can't make that determination yet, but I really want you to think about it. Who is the better athlete? Now, if you don't know anything about the long jump or shot put, one might argue athlete B, simply because there is a greater distance between their shot puts than their long jumps. But again, you're comparing apples and oranges. Just because the distance is smaller between their long jumps doesn't mean that that's just as impressive as the distance for their shot puts. Let me give you an example. I used to go to a bunch of Rubik's Cube solving competitions. Anybody surprised? No. Good. And when I went to these competitions, people usually ask, did you win? No, I did not win. I am not that good. Well, what do you have to do to win? I have to average probably about 7 or 8 seconds. Well, what do you average? About 14. Oh, but 8 to 14 seconds doesn't seem like that much of a gap. No. In the world of Rubik's Cube speed solving, it is miles and miles between 14 seconds and 8 seconds. See, the thing is, just because the distance between their long jumps is smaller doesn't mean it's not as impressive as the distance between their shot puts. What you really have to do in order to determine who is better, you have to compare them to everyone else who competed on that day. So just for the sake of argument, here is the mean distance for each event on that day. Everyone else who competed. Everyone else who competed on that day in the long jump, all together, including our 2 athletes, averaged about 6.16 meters. And everyone who competed in the shot put averaged approximately 13.29 meters. Now, we can come to a small conclusion. The small conclusion that we can come to is that both of our athletes are better than average. They're better than average. Okay. I mean, obviously, if one was, less than average, we might be able to make a good comparison there, but they're clearly both better than average. We need one more piece of information, and that is the standard deviation of the day. As a reminder, in terms of standard deviation, it's calculated in such a way where they find the differences between the data point and the average, the deviations. They square them. They add them all up. they divide by n minus 1, and they square root that sucker back in order to get what is known as standard deviation. As I have defined it in the past, standard deviation is like average deviation from the mean. Everything deviates from the mean. For example, athlete B deviates above the mean. So does athlete A. But on average, how much do people deviate? Some deviate below, some deviate above. On average, the standard deviation for the long jump was 0.23 meters. And the average deviation for the shot put was 1.24 meters. Now, what does that mean for us? Standard deviation, again, is like average deviation. Standard deviation is a measure of spread. Standard deviation tells you how spread out your data is. For example, since 1.24 is the larger standard deviation, I can confidently say that for the shot put, their data points are a bit more spread out than that of the long jump. Because the long jump standard deviation is smaller, I can say confidently that for the long jump, if I were to plot all of their points, their data points would be much more consistent and closer together. Now, what does that mean for us? Well, kind of have a formula to give you. Well, definition and a formula, which is going to help us directly compare these two athletes. Remember, we're still trying to answer that question. Who is the better athlete? Who is the better athlete? So I have to introduce to you a brand new thing that you may or may not have ever heard of before. It's called a Z-score. It's called a Z-score. Now, I've mentioned a few times so far, we need a standardized way of comparing these two athletes. We need a standardized way of being able to compare their long jumping distances to their shot putting distances. I cannot convert long jump to shot put and vice versa, but I can convert all of their distances into what is known as Z-scores. And Z-scores are a standardized ruler by which we can measure how good these athletes actually are. Let me give you a little definition here. A Z-score is a standardized measurement for data. We need standardized measurements. We need standardized measurements. For some reason, I don't know why, the United States is one of like 3 countries in the world that don't use the metric system. How messed up is that? Just saying. Do you know why they call it a foot? They used to measure a foot after this one king in this one country. They would say, oh, the length of his foot is a foot. And then every time there was a new king, they had to remeasure a foot until they realized, oh crap, maybe we should just keep it like one consistent measurement. Yeah, that might be easier. Whatever. Now, what it tells you, what Z-scores tells you, it tells you how many standard deviations, I'm abbreviating SD, it tells you how many standard deviations away from the mean a point is. I can spell point today. Point. But I'll rewrite it. A point is. The way that it's calculated is like this. Z equals X minus X bar over S. Now, that's not the only way to write it. I'm going to show you an alternative way to write it in a moment. But just for the sake of argument, I always put that little line in my Z's. That's just a habit of mine because I don't want you to confuse them with 2's. It's just a good practice. Here's another way of seeing it. There's another way of seeing it. One way of seeing it is with these sample statistics, which is what we have. All we have right now are sample statistics because it's people competing on that one particular day. But if you were comparing an entire population, to your data point, you would be using mu and sigma to represent the mean and standard deviation. Please keep that in mind. This is the standardized way. The idea is that you find the deviation between you and the mean, and you divide by standard deviation. It'll tell you how many standard deviations you are away from the mean, and it is incredibly helpful. So let's begin comparing athlete A and B. Let's start with athlete A. Athlete A. In the long jump, I'm just going to write the word long. In the long jump, if I were to plug in athlete A's information into the long jump, I would get the following calculation. X minus X bar, the data point minus the mean, divided by the standard deviation. I've already done the calculations for you, so don't worry about that. Just please keep in mind that you need to calculate these correctly. Oh my goodness. Let me just show you something real quick. Hold on, let me do it like this. Here we go. Let me zoom in on my calculator real quick. Let me just show you. Here's two different ways that I've seen people calculate z-score. There it is. It just focused. These are two different ways that I've seen people calculate z-scores. Can you tell me which one is correct? The top one. The top one is correct. Absolutely, yes. You need to put parentheses around the top of that fraction. Please. Please, by all means. I just don't want you making those mistakes because those are silly mistakes. Don't do it. But anyway, I've already done the calculations for you for these, so I'm just going to kind of move ahead with them. Athlete A had a 2.7 z-score. Now, z-scores typically don't have units on them. They typically don't have units on them because, again, this is what meters minus meters divided by meters. 2.7 is the z-score. It means that athlete A performed about 2.7 standard deviations better than average. That's what it means for athlete A. Let's look at athlete A's shot put. Athlete A's shot put, move that away, there we go, would be 14.77 minus 13.29 divided by 1.24. You get a 1.19 there. A couple of things I want you to notice. A couple of things that I need you to notice. The order in which you do this subtraction, is always the data point minus the mean. If you are better than average, then your z-score will end up being a positive number. If you are worse than average, let's say I only threw like 12 meters here, then yes, your z-score would be a negative number. If you're worse than average, you're negative. If you're better than average, you're positive. The easiest, hopefully easiest logical jump in the world. What happens if I throw exactly 13.29 meters in the shot put? What's my z-score? 0. If you hit 0 as the z-score, that means, boom, you are right on average, right in the middle. No deviation. So just for the sake of argument. Now, the thing is, I can't compare apples and oranges. I cannot compare the long jump and the shot put until I do this conversion. Because this 2.7 is 2.7 standard deviations better than the mean. And this 1.19 is 1.19 standard deviations better than the mean. They're both exactly the same unit. I mean, yes, meters, but again, you're comparing the long jump to the shot put. But once you do this conversion, you are totally allowed to add them together. You are totally allowed to add them together. Athlete A's combined z-score is 3.89. Let's look at athlete B. Athlete B, we would have to do the same calculations. And again, I've already done these for you, so no worries there. Don't panic. Let's do them together, kind of. In the long jump, this would be the calculation for athlete B. Now look at that. Athlete A in the long jump was more than 2 standard deviations above the mean. Now what that visually looks like, I'm going to show you a graph for the long jump in a little bit. But athlete B, even though athlete B was better than average, their z-score was less than 1. That may come into play. Let's look at the shot put. In the shot put, athlete B does the following calculation. Data point minus the mean divided by the standard deviation to get a 2.51. Now, yes, athlete B is an exceptional shot putter. Exceptional shot putter. 2.51 standard deviations better than the mean shot putter. But athlete A is better. Athlete A is better when you compare athlete A to all the other long jumpers on that day. The total here is 3.12. Conclusion: athlete A is the better athlete. This is evidence to suggest that athlete A is the better athlete. Athlete A is better. This is evidence. This is purely evidence, of course, but it goes a long way to kind of show, well, yeah, athlete A is better. Here's my mathematical evidence to back that up. Not my subjective standard as to what's more difficult. Now, someone asked me a really great question one time. Well, Mr. Markey, how can athlete A be better even though the distance for the long jump was smaller? Well, it has to do with that standard deviation. It has to do with that standard deviation. Because the standard deviation in the long jump was smaller, all of those distances were jumped closer together. And because those distances in the long jump were jumbled closer together, every additional 1/10 of a meter means everything in the world. Do you guys know who Bob Beamon is? How dare you not know who Bob Beamon is? So back in 1968, Bob Beamon was an Olympic long jumper in Mexico City. That's where the Olympics were being held. For the United, he was an American, and at the time, the long jump world record was being broken by like 1/4 of an inch, 1/2 an inch, like things like the very tiny distances. And Bob Beamon goes into this Olympic Games, and the world record's like, let's just say the world record's at like 27 feet and like 5 inches. I'm just making that up. I really don't know exactly what it was. And so Bob Beamon goes into this Olympic Games, and he's just like, I'm going to break the world record. He's like, but I'm not just going to break the world record. I'm going to shatter the world record. I'm going to get 28 feet, which would break it by like 6 or 7 inches. And Bob Beamon's like, I'm going to do it. So in the Olympics, he goes up, he does the jump. He felt pretty good about it. He's like, I don't think I broke 28 feet. I think I broke the world record, but I don't think I broke 28 feet. It takes the Olympic officials 20 minutes to come to a conclusion. And when they come to a conclusion, yes, he broke the world record. Yes, he broke 28 feet. He also broke 29 feet. I know. It was the single greatest athletic achievement of this generation. And most of you don't even know the name Bob Beamon. 1968. His long jump is still the second longest in history. All right, whatever. You got to know your history. Let's draw a normal curve. Not really. Let's draw a normal curve. Now what I want to do is I want to create this normal curve, this graphical display, using the long jump numbers. Oh, total side note, I'm still grading your graphical display majors. When I got back, I had like 100 or so emails that I had to go through, but I'm still in the middle of grading them. They'll make it in for the first marking period. No worries. Back to this. Right in the middle, right in the smack dab middle of this thing, I'm going to put 6.16 meters. Let me zoom in a little. I'm going to put 6.16 meters because that is the average. That is the average long jump distance of the day. And right about here, I'm going to write a slightly different number. I'm going to write 6.39 meters. 6.39. Mr. Markey, where in the heck did you get 6.39 meters? I got it by adding one standard deviation. I added 0.23. Before we left for that week off, I had shown you the basics for what is involved with a normal display. Very basic, very intro-y type stuff. But obviously now we're getting into more of the nitty-gritty of it all. This is adding 0.23 meters. Approximately the same distance right here. I'm going to add another 0.23 meters. 6.62. 6.62. I'm going to do it one more time over here. 6.85. Now, this normal curve is acting kind of like a histogram. In fact, if you took all of the data points of people in this long jump and you were to create a histogram with them, the histogram would resemble this normal curve. It may not be perfect, but it may resemble this normal curve. And if your data follows a normal distribution, then you can make various predictions about the data points. For example, if you are a data point that is within this range in the middle, you fall within the one really large chunk of data. That's where the majority of people end up falling. Even if you're better than average, it's like, yeah, you're better than average, but you were kind of close to the average. But you can see the farther distance that you jump, the less people that have actually achieved those numbers. And the farther the distance that you jump, the more amazing that your achievement actually became. In fact, I'm going to write this down a little bit later, but they typically say that if you are more than 2 standard deviations away from the mean, then you are considered unusual. You could be considered either unusually high or unusually low. Most people fall within 2 standard deviations. I'm going to get into those details again in a little bit with the definition that I have. We'll get there. Let's go the other way. 6.16 minus 0.23. I'm going to go the other way. Going the other way, I am subtracting 0.23. Subtracting 0.23, 5.70, and subtracting 0.23, 5.47 meters. This is the normal distribution of all of those long jumping times, with your mean right in the middle and everyone else kind of to the sides, either less than average or better than average. I wrote these numbers last time. I want to do it again. If you fall between +1 and -1 standard deviations, you fall within the middle 68% of data points. If you fall within +1 or -1 standard deviation, you are within the middle 68% of data points. If you fall within +2 or -2 standard deviations away from the mean, that is the middle 95% of data points. And this typically happens when you see these displays, but people typically don't have room to do the next one. So they usually write it like underneath. But if you go from +3 to -3 standard deviations, you fall within the middle 99.7% of data points. Those numbers are pretty consistent. Those numbers are estimates. They are estimates, but they are pretty consistent from one normal curve to the next. I believe I wrote this down again last time. I want to do it again. This 68, 95, 99.7 rule is known as the empirical rule. Empirical rule. I don't know how to spell empirical. Whatever. Empirical rule. Let's just assume I spelled it correctly. I'm a math teacher. Whenever you hear the empirical rule, they're referring to these numbers, the 68, 95, 99.7% rule. Now, obviously, this normal curve is symmetric. This normal curve is symmetric. And by the way, athlete, who was the better long jumper? Athlete A? How long did they jump? 6 point what? 6.78. So 6.2 right here. That's fun. There's athlete A right there. Now, here's something that we can say about athlete A. Yes, athlete A was more than 2 standard deviations away from the mean. What was it, 2.70? Yeah, for a Z-score. Now, athlete A does not exist in the middle 68%. Athlete A does not exist in the middle 95%. Athlete A actually exists in this top percentile. I'm not going to use the word percentile just yet, actually. I'm going to save that for another time. But athlete A exists in this top percent type group. I just shaded in this area. Now, again, between these two dotted lines right here, there's 68% of the data. Between these two dotted lines is 95% of the data. What percent of the data does athlete A fall into? I could say athlete A falls into the top blank percent of the data. What would you say? Ooh. Think of it this way. This marker might be a little better. Yeah, it is, totally. I'm going to erase all this in a moment, just keep in mind. But if I were to shade in all of this in the middle, if I were to shade in all of this in the middle, that would account for 95% of all data points. All of that in the middle is 95% of all data points. What's this section right here? What percentage of the data is that section? Take a guess. 2.5. See, the thing is, athlete A falls in the, I'm going to be very clear with my words. Athlete A falls in the outside 5%. The outside 5%, because 95% is in the middle. But more specifically, athlete A falls in the top 2.5%. That's a terrible 2.5 that I just drew. In the top 2.5%. Athlete A is considered unusually good at the long jump. Unusually good is what ends up happening. There's a lot of symmetry that kind of goes on with this. It's really interesting the way that it happens. For example, here's an additional question for you, and you can figure this out in your head. You can figure this out in your head. I'm between a z-score of 0 and a z-score of 1. I'm between 6.16 meters and 6.39 meters. What percent of the data points did I just shade in? 34. You can do it in your head. You can do it in your head. That's 34%. Because 68% is in the middle, and it's supposed to be symmetric. It's 34% right there. This one gets a little trickier. Just slightly trickier. Just slightly trickier. And after this, I'll kind of show you something else. This one's just slightly trickier. Slightly trickier. What do you think? It would not be 1/4 of 95. Because the area, think about it like shaded in area, like geometry. The area of this region is not equal to the area of this region. They're different heights. So it would not be 1/4 of 95. What'd you get? 13.5. Because, and I'm going to assume this is what you did, because I know how it's done, obviously. What he did was, he said, okay, between here and here is 95%. So he did 95 minus 68, which is that middle portion right here. And that's 27. So between this region and this region, that's 27%, and you cut it in half. Yeah. Just little things like that. Just little things like that. Again, we'll have more practice with it. This is just your introduction to everything, kind of, so to speak. Oh, weirdness. Oh, weirdness. Okay. Couple of things about the normal curve that I need you to be aware of. A couple of bullet points that you need to keep in the back of your mind. Here we go. Bullet point. If you have a normal distribution, then you must think in z-scores. If you have a normal distribution, then you must think of it in terms of z-scores. Now, not to give you all PTSD, but you all remember geometry? Okay. Some people rolled their eyes. I saw it. In geometry, I don't know the answer. What was it called when you could read a statement like if then, and then you reversed it and it was still true? Was that something you learned in geometry? Huh? It was kind of like a condition, but there was like a special name for it, right? Like what? No, this is not the answer, but it was like one of these terms was like contrapositive or some junk like that. But that's not what this answer is. Maybe it wasn't conjecture. I want to say converse, but I'm thinking sneakers. I don't know. Geometry is weird. Y'all have PTSD from geometry? Yeah, bro. Anyway, here's the thing. The reverse is true. If you're in z-scores, if you are being told to work with z-scores, then your assumption is that you have a normal distribution. They go hand in hand with each other. It's kind of nice. It's really kind of nice. So what this thing typically does. Couple of other bullet points that I need you to have right here. More than 2 standard deviations away from the mean is considered, quote, unusual. More than 2 standard deviations away from the mean is considered unusual. It's considered either unusually high or unusually low. Again, somebody asked me an amazing question last year. They said, Mr. Markey, so is this very similar to being an outlier? And I said, great question, 2 different definitions. See, the thing is, if you're going to be considered unusually high or unusually low, then by definition, you are more than 2 standard deviations away from the mean. But if you want to label a data point as an outlier fits this definition of being outside the range Q1 minus 1.5 IQR, comma Q3 plus 1.5 IQR. That is the definition of being an outlier. This is the definition of being unusually high or unusually low. And it seems like that's just a ridiculous distinction. It is. But when you're dealing with AP statistics and these questions that they're going to throw at you, I want you to be very aware that these two definitions don't play well together. They prefer to keep them separated. So if you ever have a question that refers to a data point as being unusually high, I want you to immediately think, okay, it's more than 2 standard deviations above the mean because it's unusually high. Or if they say, no, this data point, this really small data point, it's an outlier, then I need you to think, okay, if outlier, it means that it's less than Q1 minus 1.5 IQR. We need to have that clear distinction there in the verbiage that they choose to use. Let's see. Okay. As long as your data is, quote, nearly normal, end quote, then using z-scores is appropriate. See, the thing is, there's going to be certain assumptions and conditions that you will eventually have to deal with. And one of those assumptions and conditions is the nearly normal condition. It's not that your data has to be perfect. It's not that your data has to look perfectly normal when you look at the histogram. It just has to be close enough. And not a lot of people are very comfortable with that. Not a lot of people are comfortable with that. Back in the day, did you guys ever do like scatter plots and like lines of best fit? Yeah. There's going to be a condition in those chapters where it's like, okay, look at the scatter plot. Do the points look straight enough? Like, what do you mean does it look straight enough? What kind of definition is do the points look straight enough? I'm not even kidding. That's literally the definition. As long as it looks straight enough, then a linear regression is most likely appropriate. It's so weird because, again, they use a lot of fluffy language. Okay. Now, here's the thing. I'm not going to ask you to break out the calculators right now, only because I have the calculator on my phone. I don't want to use the 83. I want to use the 84 because this is what you are going to be familiar with. Actually, you know what? I'll use both just for the sake of argument. Zoom out. Hopefully, I don't get any messages. Now, I'm going to show you something in the calculators. Then I'm going to write this stuff down. I just need you to see it first. In your calculators, there is this button that I'm pointing to right here called VARS. V-A-R-S. Variables. But what I'm really more interested in is what's written above it in yellow. Now, on your calculators, on your Chromebooks, I believe it'd be written in blue or whatever. But what's written above it is some kind of weird abbreviation of the word distribution. And if you hit second VARS, I'll do it over here, second VARS, it brings you to this screen. It brings you to this screen. Second VARS brings you to this screen. Now, again, you can click, oh, normal. That's probably what we're interested in. Yes, it is. I'm actually interested in 2 specific functions on this screen. I'm interested in normal CDF, and I am interested in inverse norm. I am not interested in normal PDF. We're not going to be using normal PDF this year at all. Not normal PDF. We'll use a PDF later on, but not for this. That's for like 3rd or 4th year statistics students in college. The PDF stands for probability distribution function, and the CDF is cumulative distribution function. We're focused on the cumulative one. Eventually, you're going to get to other things on this screen. We're eventually going to use the t's. It's going to be super fun when we get to the t's. And then eventually, we're going to go a bit farther, and we're going to use the binom, and we're going to use the geomet. It's going to be so much fun. By the way, do you see that P word? Do you know how to pronounce that properly? It's anyone taking French? There you go. Yeah, it's French. It was named after a French mathematician. I don't know. It's the only good thing French people have ever done. So it's okay. I tell Madame Morris that all the time. Anyway, back to this. What I'm really interested in is this normal CDF, and I'm going to show it to you on both screens. Oh, no! Because I just need you to be aware of it. If I hit enter on my 83, this screen pops up. If I hit enter on my 84, which is what you have, this screen pops up. I need you to be aware of both. Now, what ends up happening with the 83 on the right is that if I just type in what is here, like -1 to +1, and hit enter, I'm going to get the exact same answer as this. Look, mu and sigma. Let me draw a little picture here. If I were to do a normal curve with mu as 0 right in the middle and sigma as 1, what it's actually creating is a normal curve made up of nothing but z-scores. That's all it's doing. It's just creating a normal curve of z-scores. For the TI-83 calculator, if I just type in -1, 1 and just hit enter, the 83 calculator is going to assume that those numbers are already z-scores. It's going to assume they're already z-scores. If I just leave this as is and go to paste on the 84, which is what your calculators would do, you can see it just pops in those numbers right there and has the 0, 1 there. Chapow, chapoom. Empirical rule. What percentage of the data is between -1 and +1 z-scores? 68%. Now that's an estimation based on a calculation done over 500 years ago. This is the actual number. This is the actual number. It's very strange. Dylan, you said the answer before was 13.5? Check this out. I could do this again between +1 and +2, which would have given you that 13.5%. Now, that is based on the empirical rule. This is the actual number based on pure calculations. The empirical rule is an estimation. The empirical rule was the best that we could do until the advent of modern technology. Modern technology was actually allows us to get the exact number. So just for the sake of argument. Now, normal CDF is going to help us a lot. Check this out. I'm going to do this on both screens. Normal CDF, good. Now, I'm going to go back to my long jump example. And I'm going to say, okay, what percentage of the data falls between, and actually let me go to my normal curve real quick. The one that I drew. There it is. What percentage of the data falls between 6.39 and 6.62, given that my mean is 6.16 and my standard deviation is 0.23? You can see hopefully how I typed that in. Let me do it on the 84. What percentage of the, oh, I didn't put a comma there. Comma, there we go. What percentage of the data falls between 6.39, I don't need a comma, 6.62, given a mean of 6.16 and a standard deviation of 0.23. I want you to see how this is done. Because our data for the long jump was normally distributed, I'm literally trying to find the percentage of the data that falls between these two data points, given that I have a mean of 6.16 and a standard deviation of 0.23. On your 84s, you would type it in like that. On my 83, I would have to type it in like this, in that exact order. Now, I picked the exact answer that we had from before with that 13.5. Get rid of this. What I picked were data points right here between +1 standard deviation and +2 standard deviations. So this should give me approximately 13.5%. It'll probably round up. There it is. Go down to paste, hit enter, and there it is. That's what this normal CDF allows us to do. That's what normal. And again, I'm going to have you write this stuff down in a little bit. Let's go to the other one that I want to talk about. Inverse norm. Inverse norm. When you think of the word inverse, what do you think of? What is an inverse? You're just rolling your arms. I couldn't hear you. Reverse? Yeah, I would think of that. Kind of like going backwards. That's why you're doing that. You weren't just dancing. Okay. If I go inverse norm, look what pops up here. See, it's the backwards portion of this whole thing. What inverse norm actually allows you to do, instead of typing in the data points and getting an area or a percentage, you type in the percentage and it spits you back a data point. It does the exact opposite. I'm going to show you how it works. For example, let's try to figure out what's a good percentile. If you're in like this top percentile, what's a good percentile? Like, don't pick like the 100th percentile. There's no such real thing as that. Like maybe like the 84th percentile. No. If you're in the 84th percentile, that's pretty good. Good for you. All right. Let's pick the 84th percentile. Now, if we're picking the 84th percentile, I'm going to type it in as 0.84. 0.84, comma. Now, I'm going to stick with the long jump. I'm going to stick with the long jump for a moment, because if I just hit enter right now, that's what it spits out. If I just hit enter right now, that's what it spits out. What the heck is that? What that is approximately right there. That's the 84th percentile. Just under one z-score. Just under one standard deviation above the mean. That's what that 84th percentile actually means. And that's not what I wanted. I wanted to actually type in the mean and standard deviation of the long jump. Let's bring that back. The mean was 6.16. The standard deviation was 0.23. Yeah, it's 0.23. I'll do it here. 6.16, 0.23, paste, enter, enter. What that basically means is this. If you're existing at the 84th percentile of these long jumps, the 84th percentile data point of this long jump is approximately 6.39 meters. And again, I did that on purpose because it's approximately one standard deviation above the mean. Approximately. Oh, it's so weird. You're going to get used to these functions, trust me. Let's go back to our notes. So I want to write down some of this information. So let's get there. Let's see. Here we go. Zooming out. So let's talk about normal CDF. Normal CDF, parentheses. Now I'm going to say lower limit, upper limit. And I'm going to leave it like that for a moment. It gives the percent of data points between two z-scores. If you just simply put in two numbers, a lower limit and an upper limit, it would give you the percentage of data points between two z-scores. And I specify z-scores because I did not put in a mean or a standard deviation. Whereas, if I actually typed it in with a lower limit and an upper limit and a mu and a sigma in that order, if I actually typed that in, it would give, or it gives, the percentage of data points, between two data points. Whatever the context of the situation is that you are dealing with. Whereas in this case, we're dealing with the long jump distances. If you're dealing with the long jump distances, then it would give you the percentage of data points between those two long jump distances. Let's see. Just as another example, and I'll show you this in a moment on my calculator. If you went normal CDF, some really small number, or not some really small number, but some really like giant negative number, like negative 100,000, comma, I don't know, some number K, whatever number K that is. I don't know what that is. Actually, no, let's replace K. I'm going to replace K with Z, and I'm doing that on purpose. I'm going to replace K with Z. Z. There we go. Much better. Check this out. It's going to be really crazy. It gives the percentile of that z-score. It gives the percentile of that z-score. I'm going to show that to you right now. Now, that negative 100,000 doesn't really have to be anything. I mean, it could be like negative 1 billion. It could be just some giant negative number. Let me show you what it looks like here. If I did normal CDF negative some giant number, comma 1, it gives me approximately the 84th percentile. I want to be very clear about that. Percentiles are calculated obviously slightly differently, but it would have filled in 84% of that thing. Just very quickly, I just want to get in here. Inverse norm. Inverse norm, if you type in the percentile, it gives the z-score at that percentile. And again, that percentile I would put in as a decimal. And of course, you can do inverse norm, percentile, comma, mu, comma, sigma. And it doesn't give the z-score at that percentile. It gives the data point in context at that percentile. I need you to be very familiar with how to actually use those functions in the calculator. They are going to come into play a bit moving forward. Okay. Now, like I said, I'm still wrapping up your majors to get in for the marking period. The marking period ends this week. Grades are due next week. And we'll get moving with it. Pay attention to Google Classroom, and we'll see what happens from there. Woo! I'll see you guys actually when? On Tuesday? Okay, whatever. No one's excited. Except for me.